Space, the final frontier. These are the voyages of the starship Enterprise. Its 5-year mission: to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.
Good morning. We start on a new chapter today, Chapter 9, Counting and Probability. This is a very interesting chapter. It's also a kind of a long one, and I'm going to try and make it easier for you. You will note on the web page I've also given you some reference to some material to read that isn't in the book, and you might want to start off reading that first, and maybe that'll make some of your reading in the book a little bit clearer. So the topic or the chapter title is called Counting and Probability. The real goal here is probability, but it turns out to calculate lots of interesting probabilities, we have to know how to count. People are very surprised to hear that, but it turns out that counting things is not always that easy. And we're going to see some examples of things in this chapter where it turns out that counting is not so easy. But we're going to start off with a simple example here, and this is the same example in your book. I want to go ahead and I want to flip a coin. I want to flip actually 2 coins. Now, I don't recall in Namibia if you make the distinction that we do here in the United States with coins. There are 2 sides to a coin, and here in the States we talk about there's one side that's called heads, and that usually has a picture of somebody on it. And the other side of it is called tails. And here in the U.S., again, that typically has a picture of a building on it. So that little squiggly thing that you see right there, that's a building, in case you couldn't tell. And we're already going to jump into probability theory. We're going to assume that it's a fair coin. And what a fair coin means is that if I flip the coin, whatever side comes up is equally likely. In other words, I'm going to say that the probability of heads is equal to the probability of tails, and that would be 1/2. And one of the axioms of probability, and we'll be talking about this later, if we flip a coin, we note that only one of 2 things can happen. It can only be heads or tails. And it is always the case that if I take the probability of all the possibilities that can happen, they have to sum up to 1. So we get that point right over here. And I think that you all knew that. Now, what we're doing here is we're doing something a little bit different. We're going to flip the coin twice. And what we want to know is that when we are done flipping the coin twice, what is the probability that the total number of heads I observed is 1? Well, what I want to do here is I want to consider how many different possible outcomes are there? And I come over here and I make a little table and I say, well, look, I can flip the first coin and get a head, and then I can flip the second coin and I can get a head. And I'm going to refer to that as head, head. Again, the first coin could be head and the second could be tail, so that's going to be head, tail. The first coin could be tail. The second coin could be head, so that's tail, head. And again, if the first coin is tail, the second coin could be tail, so here's tail, tail. So notice that there are a total of 4 possibilities for outcomes of flipping 2 coins. So what I'm going to create here, which your author refers to as a sample space. And notice that my sample space is made up of these 4 tuples. Now we have to be a little bit careful here about our notation. A sample space is a set. So notice that on the outsides here, I have in fact used the squiggly brackets that indicate a set. But inside, notice that my elements of the set are ordered pairs. In other words, inside there is a difference between HT and TH. Okay, this is the situation where I had a head followed by a tail. This is the situation where I had a tail followed by a head. So what my sample space is my sample space is a listing of all of the possible outcomes I get from performing my experiment, which is at flipping 2 coins. Now the question here is what is the probability that the total number of heads I see is 1? So that corresponds to a specific event, okay? And again, an event is going to correspond to a subset of the sample space. In other words, what I'm interested in is what is the probability that I saw either head-tail or tail-head. These correspond to the possibility of seeing just one head. Okay, let us continue. So again, just repeating what we had before, our event set corresponds to HT and TH. Here is our space, our sample space, which corresponds to these 4 items. And we get that the probability of one head, and here I'm using the notation that your author uses. N of E is referring to the number of elements in E. Well, E has 2 elements in it. N of S is 4. There are 4 elements. So this probability over here is 1/2. And I just want to note that your author has used this notation N of E. You'll also sometimes see people use this notation here. They'll put the absolute value signs around the name of a set to denote how many elements are in the set. So this is a very quick introduction to the types of problems we're going to be considering in this chapter. Let's consider a couple of other examples that they talk about in your book. Let's consider the experiment of rolling a die. Okay, now I assume you all know what a die is. It's this cube. And it's got a 1 over there, and it's got 2 over there, and I can't draw all the faces, but there's 1, there's 2, there's 1, 2, 3, 1, 2, 3, 4. It's got 6 sides on it. These are the 6 sides of the die. So again, we are going to assume that it's a fair die, and remember what a fair die means. A fair die means that any one of these 6 sides is equally likely. So in fact, the probability of any one side is 1/6. Like that. And now we might consider the experiment. And I'm going to say roll the die twice. Or roll 2 dice. It's the same either way. Now the first thing I'd like to talk about are how many possible outcomes are there. Well, again, you could think of this as being an ordered pair like this. And this would be outcome 1. And over here, that's outcome 2. And what your author likes to do is to say, well, look, for outcome 1, I could have a 1, and then over here, I could have a 1, or I could have a 2, all the way down here to 6, and then I could do the same thing with 2, and I could do this all the way down to 6. In other words, I could come over here at 6, and over here I could have a 1, and over here I could have a 2, and this could go all the way down to having 6. So we will notice that for each one of these, there are 6 coming out of here. Okay, for 2, there would be 6 coming out of here. And there are 6 of these. So the point is for the first, in this tuple here, I could have 6 over here, and then for any one of the second ones, I could have 6 over here. So the total number of these would be 36. You could see they're going to be 6 here, they're going to be 6 here, all the way down to 6 here. There are a total of 36 different possible outcomes. So if I were to say to you, for example, what is the probability of rolling a 3? Well, there are 2 ways to roll a 3. One way to roll a 3 would be to roll a 1 and a 2. And the other way to do it would be to roll a 2 and a 1. So using the notation that we had before, E would be equal to this set right over here, okay? And this over here, by the way, this is our sample set. In other words, these 36 possibilities constitute all the possibilities of outcomes from rolling 2 die. So the probability of rolling a 3 is going to equal n of E over n of S, and that's going to equal 2 over 36, or it's equal to 1/18. Okay? And I ask you as a homework problem, what outcome is most likely? Well, that's not too hard to figure out. Remember that when you roll 2 dice, the smallest outcome you could get is a 2. The largest outcome you could get is 12. Okay, I'm adding up the total number of adding the 2 dies. And so you just need to figure out the probability of 2, the probability of 3, the probability of 4, all the way up to the probability of 12, and to see which one of these is the biggest. Okay? Now, I want to talk about something here. Remember in the first case we flipped 2 coins. And in this other example here, we rolled 2 dice. And what I want to do is I want to consider a couple of other things. Suppose I flip 3 coins. Or suppose I roll 4 dice. And we could continue this on and on and on. Well, the question is how big is the sample space? And that's what I want to talk about here. Now, remember, if I'm flipping 2 coins, my output can be specified as an ordered tuple like this. And if I roll 2 dice, again, my output can be specified as an ordered tuple. If I flip 3 coins, well, I've got the output of the first coin, the second coin, and the third coin. If I roll 4 dice, well, the first die, the second die, the third die, and the fourth die. Now, just notice the following. If I flip 2 coins, there are 2 possibilities for the first coin, and there are 2 possibilities for the second coin. And I multiply those 4. Or I'm going to say, or 2 squared. If I roll 2 dice, well, remember, for each die there are 6 possibilities. So that's equal to 36, or 6 squared. If I flip 3 coins, there are two possibilities for the first one, two possibilities for the second one, two possibilities for the third. And again, what you can do is you can make a tree here. Okay, and you can finish up the tree to see what all the possible ways of doing this are. But this is equal to 2 to the third. If I'm going to roll 4 dice, for each outcome, there are 6 possibilities here. This is equal to 6 to the fourth. So I hope you're seeing a pattern here, okay? And in fact, if we're keeping track of, I'm going to say a k-tuple, which is another way of saying repeat experiment k times, and each experiment has R outcomes, then the size of our sample space is going to be what? Well, it's going to be R to the K. Okay? And in your book, your author refers to this as the multiplication rule. Well, this is one version of it. Okay, we're going to leave the book for a second, and I'm going to talk to you about something that's related. This also was in the webpage that I referred to you, and I want to talk about these things that are called permutations. These are very important. Permutations. And the other thing that we're going to hear about later on are these things called combinations. And these are related ideas. People have trouble remembering the difference here. Permutations, you need to remember the word position. Position matters. So that when you talk about permutations, you're talking about ordered tuples. In other words, I come over here and I say AB, and notice I'm using the round brackets over here, and we know that that's not the same thing as BA, because the order matters. Combinations here, position doesn't matter. And what happens over here is the notation are usually sets. So for example, we know that the set AB is exactly the same thing as the set BA. Okay, so keep these two words in mind, and for the moment we're talking about permutations. Okay, so now I want you to think about the following. I want you to suppose that I have 3 tuples over here, and I want you to suppose that over here I have a bag, okay, and inside of this bag there's a square, and there's a triangle, and there's a circle, and I don't know, there's a little stick man like that. Okay, so notice over here in this bag there are 4 different things. And what I want to do is I want to do an experiment. And the experiment goes as follows. I stick my hand in the bag, I don't take a look, I grab something, and I come over here and I put it here. And then I record what's there, and I take what's here and I put it back in here. And then what I do is I go ahead again, I grab in the bag here, and I grab something, and I come over here, and I record what it is, and then I pick this thing up, and I put it back in here. And then what happens again is I grab one more thing, and I put it over here, I record what it is, and then I put it back over here. Now what I've just described to you is what's called sampling with replacement. Okay, and again, remember what that does. I'm pulling one thing out of here at random, I'm sticking it in the appropriate spot, and then after I record it, I put it back in here. So again, the question I have is, how many different unique three tuples can I get here? Well, again, we can see that there are 4 different possibilities that I could put over here, and then there are 4 possibilities I could put over here, and there are 4 possibilities I could get over here. So this would be equal to 4 to the third. So we could imagine what these things might look like. Like I might have something that looks like this. Here's a square, square, triangle, and then if I were to come over here, I could have stick figure, comma, square, triangle, and you could imagine all of the possibilities here, circle, circle, triangle, and this is going to go on for quite a bit. And in fact, if I were looking at this as my sample space, it's going to be pretty big. It's going to be 4 to the third. That's 16 times 4. That's equal to 64. And I'm not going to bore you by listing all 64 of these things, but you could see that, in fact, that's how many of these different three tuples there would be in here. And this just follows from our rule that we gave before when we were looking at flipping the coins or rolling the dice. So when we're flipping the coins or rolling the dice, remember, there is the possibility that we could repeat something. For example, over here we repeated the square, or over here we repeated the circle. So that when you talk about flipping a coin or rolling a dice, that's equivalent to talking about sampling with replacement. Okay? Well, that's not the only way that we could sample. Let's come over here and let's get a fresh screen to write on. So again, let me see what's in here. We create my bag of objects in it, and we have the square in it, and we have this in it, and the circle, and we have our stick figure. Okay. And now what I want to do is I want to sample without replacement. Okay, and again, I want to consider that I've got these 3 places over here. So now what's going to happen is I'm going to reach in here and I'm going to grab one of these things and I'm going to put it over in this spot here. But now what I'm going to do is I'm going to leave it there. I'm not going to put it back in here. So if there were 4 things to choose from here, now when I come over here, there are only 3 things to choose from. Okay, and again, I'm not going to put it back in. So then there are only 2 things to come over here. So it turns out that I could have 4 things here, and there'd be 3 things here, and there would be 2 things there. That's 4 times 3 is 12. There are 24 of these. Okay, so again, an example, if I were to consider the if I were to consider the sample space here, I might have this, or I might have this, or I might have this, and this would go on, and there would be a total of 24 of these. Now, I want you to consider the notion, I want to consider how are we going to, what's the notation for this? So notice what we've done here. I think you all may remember that if I write this thing n factorial, that's equal to n times n minus 1 times n minus 2 all the way down to 2 and then 1, okay? What we have over here is something very, very similar, and in your book they actually refer to this as P of nk, and what that's equal to is that's equal to n times n minus 1 times n minus k plus 1. Now you may be a little bit confused here about this. So in other words, what we're doing over here is this is equal to P of 4 comma 3. Okay? And remember, the 4 is referring to how many items there are in the original bag here that we're going to be sampling from without replacement. The 3 is referring to how many of these slots we have over here. Well, you can see that our definition over here, P of 4 comma 3 is going to be equal to 4 times 3 times, and we go all the way down to 4 minus 3 plus 1. Well, this number right over here is 2. Okay? So you need to remember that. So remember, if we have n items and k samples from the n items, okay, if we are sampling without replacement, then we have P of n comma k, and if we are sampling with replacement, it's just n to the k. So these are formulas that you need to keep in mind. Now, let's consider a couple of things here. Let's look at an example. Let's see, when I am in Namibia, I have a cell phone and I use MTC. So MTC means that my telephone number begins with 081, and then there are 3 spaces over here, and then there are 4 spaces over here. Okay, so one question I might ask is, how many MTC numbers are there? Well, okay, so take a look. In every one of these spots right here, I could put the digits 0 through 9. There are a total of 10 digits. So I could put 10 in here, 10 here, 10 here, 10, 10, 10, 10. So the answer to this would actually be 10 to the 7th. Notice that that is sampling without replacement. So we get 10 to the, that is I'm sorry, that is a mistake. That is sampling with replacement, because we could have numbers that repeat. So suppose I were to say something like the following. How many MTC numbers have no digits repeating? Well, again, so we'd have this, 2, 3, 4, 5, 6, 7. Well, I could put 10 possible digits here, and 9 there, 8, 7, 6, 5, and 4. So that this is actually what? P of 10 comma 7. Okay, that's how many would be non-repeating. Suppose I were to ask you, what is the probability an MTC number has no digits repeated. Well, we know that the size of the sample space, we just did that before, is 10 to the 7th. And we know that the size of the event space here, we just figured it out here, that's p of 10 comma 7. So the answer to this would just be p of 10 comma 7 over 10 to the 7th. And we could go ahead and figure that number out. Let's consider another example here. How many MTC numbers begin with 1, 2, 3 and end in 9? So think about that. We're talking about an MTC number that looks like this. So I'd have 1, 2, 3. And then there's 1, 2, 3, 4. And it ends in 9. So we can see that there are 10 possibilities over here, and we could see that there are 10 possibilities over here, and we could see that there are 10 possibilities over there. So the answer to that would be 10 to the 3rd. Greetings, some more counting here. This is in your book. It's going to seem a little out of place here. Counting continued. Okay, let's consider the following. Suppose I were to give you the numbers 1, 2, 3, 4, 5, 6. And I were to say to you, how many numbers are there here? May seem like a very silly question, but there are 6 numbers. In other words, if this were a set, this were equal to some set S, and I were to say to you, how big is S? You would come over there and you'd say there's 6 elements in there. That's pretty easy. But now let me pose a slightly different question to you. Suppose I were to say 17, 18, 19, 20, 21, 22, 23. And I were to say to you quickly, how many numbers are there? Well, here's the way I think about it. These are consecutive integers, and I see the number 17 there. What I'm going to do is I'm going to come over there and I'm going to subtract 16 from that. And what I'm going to do is I'm going to come over here to the last number, and I'm going to subtract 16. And I go, well, 17 minus 16 is 1. And I go, 23 minus 16, that is 7. Well, from 1 to 7, there are 7 numbers. So I know that in this set over here, there are 7 numbers. 1, 2, 3, 4, 5, 6, 7. Everybody follow that? So if I were to say to you, how many numbers, how many integers between 103 and 197 inclusive, meaning I'm including the endpoints. And I go, I don't know, but I'm going to come over here, and I know that if I subtract 102 from this, and I subtract 102 from this, I'm going to get 1 over here, and here I'm going to get 5, 9, and that says to me, you have to say, The answer is 95. Okay? Likewise, if I had an array, and suppose my array is called A, and maybe this is at 23, and this is at 24, 25, 26, 27, and I want to know, okay, I've got A23 through A27. And I go, well, how many numbers are there? Well, I don't know. I'll subtract 22 from both of them, and that gets me from 1 to 5. So what's going on here is there are 5 numbers in there. This is a very useful thing to know. So specifically, if m is less than n integers, and I want to know, I've got m plus 1, m plus 2, all the way up to n, and I want to know how many integers are there in this sequence here. Well, I would subtract m minus 1 from this, and m minus 1 from that, and I'd subtract, and here I'd get 1, and over here I would get n minus m minus 1, and remember this is just n minus m plus 1. So this is how many integers there are in this range right here. So your author comes up with a lot of, I don't know if they're interesting questions or not, but he says something like the following. How many integers between 100 and, let's say, 299 are divisible by 5? Well, 100, that's 5 times 20, and I've got 105, that's 5 times 21, and 110, that's 5 times 22, and I take this all the way up to 295, and 295 is 5 times, and let's see, I think that's 59. Yes. So now the question is, well, look at this. I've got 5 times 20 through 5 through 59. How much is that? Well, I look at this 20 and I go, well, I'm going to subtract 19 from that. And I'm going to come over here, I'm going to subtract 19 from that. And that gets me from 1 all the way up to 40. So how many integers between 100 and 299 are divisible by 5? And the answer to that is 40. Okay? I refer you to your book. Your author gives you lots of other examples of problems just like this. All right, we're going to finish up this video, at least this one, counting sets. This is not hard. Suppose I have a set A, and it's equal to 1, 2, 3. And I have a set B that's equal to 5, 6, 9, 23. And I want you to note the following. Note that the intersection is the empty set. They don't have any elements in common. So the question I have is, how big is A union B? Well, first of all, notice that A union B is just equal to 1, 2, 3, 5, 6, 9, 23. And notice that that is just equal to, here's A over here, here's B over here, so that the size of this set, this is just equal to the size of A plus the size of B. Okay? But the important thing here is that the intersection of these sets are empty. Suppose I had the following, though. Suppose A is equal to 1, 2, 3, 4. And suppose B was equal to 3, 4, 5, 7. Okay? Now, A union B is equal to 1, 2, 3, 4, 5, 7. See, the problem here is now there's a non-empty intersection. Here's A over here, here's B over here, and here's the part where they intersect. And what's happening is if we were to use this formula over here, we would count A intersection B twice. And that's not good. So it turns out that if A intersection B doesn't equal the empty set, then the size of A union B is equal to the size of A plus the size of B minus the size of the intersection. Just like that. And this is a very important fact to keep in mind. By the way, you could even say that this formula over here is always true, okay? If the intersection is null, then this thing over here is just going to be 0. So if you don't want to remember that case, you can just remember this case right over here. Now, we can extend this to the following. Suppose we were to talk about how big is A union B union C. And I am going to claim, and I'll leave it as an exercise, okay, it's the size of the individual sets, but now what you've got to do is you've got to subtract out A intersection B minus A intersection C minus B intersection C, and then you need to add this. So this formula here is a little more complicated, and I ask you to verify this. Verify this. And you could do this in a couple of ways. You could try verifying it with Venn diagrams, or you could try verifying by making some substitutions. But I will leave that as an exercise.